So, good day to everyone. Today we will discuss operation of shunt-wound and series-wound DC motors. To do this, we have this test bench. Also, we are able to control various currents, as well as we can see various measurements. So, once again, here is the DC motor. Its output shaft, this is the output shaft, yeah? Its output shaft is further connected with the brake. Yeah? So this disc is the brake disc, and the brake in our case is an electromagnetic brake, so it has no any friction. Yeah? It's fully, how to say, non-contact. Yeah? These are two electromagnets, and these magnets produce magnetic flux which flows through this disc, and in this disc we will, in this case when it will rotate in this disc, we will introduce vortex currents, and therefore these vortex currents will produce braking torque. This braking torque starts to deflect our brake. Brake is not spring loaded, but it has mass. Yeah, this is the mass. So again, we have arm, yeah, and we have mass, so we have torque, and torque is displayed here. Of course, I am able to control current through the brake, and this can be done by means of this rheostat. This is the minimum, and this is the maximum. Okay. So, this test bench allows us to select what kind of motor we will test, shunt-wound or series-wound. In real life, you are not able to make such selection because motor typically is made only shunt or only series-wound. But this motor has been modified. We have placed additional series winding inside, so we can select shunt or series. Okay, but in real life it is shunt-wound only. So we will begin with the shunt-wound motor. As you probably know, the shunt-wound motor receives power from some DC source. In my case, this is like a battery, but of course in my case I will take power from the wall, in this one. Okay, so that DC power, its output voltage can be measured. Here is the voltmeter, so I can measure the voltage. Now it is disabled. Further, this voltage is applied to the armature. This is the armature. Armature, of course, has its own internal resistance, which is shown here. RA, this is armature resistance. Armature current flows like this, and armature current can be measured by means of this ampermeter. So armature current can be measured by means of this ampermeter. This is the shunt-wound motor. So here is the field winding, which is shunt. Shunt or parallel. What means parallel? It is parallelly connected with the source, like it is done for the armature winding. That's why it is shunt, called shunt or parallel. Also, we can measure field current, which will be shown here. The final voltmeter is used to determine speed of the motor. So this motor is equipped with tiny DC generator, which is on the common shaft with the motor. So this is the tiny DC generator with permanent magnets. This is the permanent magnet. So its output voltage is directly proportional with the speed. So when we will see here 1 volt, it will mean that we are operating at 2700 RPMs. About the control. Here we are able to control field current. This is done by means of this rheostat, again minimum and maximum. And also we are able to limit armature current by means of this rheostat. This is this one. Again, minimum and maximum. So again, brake, armature current, and field current. So now let's start. Oh yeah, and I forgot to say that here on this disc I have this reflective paper, so I can measure its speed also slightly more precise by means of this measurement unit. Yeah. By putting light onto this reflecting paper. Okay, so now first of all let's start our motor. To do this, shunt wound field motor should to be started with maximum field. Why? This is because torque of DC motor is defined by the current which flows through the armature as well as by the field, whereas the field is defined by the field current. So in order to get more or less high starting torque, we have to keep field current as high as possible. So let's increase field current, and I will increase it up to the maximum. This is the maximum, final position, maximum. Okay, so now I can start to apply voltage. Full voltage, 20 volts. Okay. Now our motor is working without torque, without the brake. So now it is working at no load. So let's see. Now we are at no load, so torque is 0. But the motor still consumes some power, some current, therefore also some power. And this current is 1.2 amperes. This current is used to overcome friction in ball bearings in the motor. What about the speed? 2300. Okay, now I will increase load by means of load rheostat. Let's say to 0.2, because 0.4 this is the rated torque. 0.2, okay. As you probably can hear, the speed of the motor was slightly reduced. So, torque 0.2. What about consumed current? We apply torque, so we start to consume more. Now, consumed current is 3.2 amperes. This is also can be explained from this equation. When we start to consume torque, the armature current also should to rise up. And this can be seen from here. What about the speed? Uh, 2200. Okay, so as you can see, speed starts to drop slightly. Speed is defined by the supply voltage, but it is still 20 volts. Field, but field is defined by the field current and it is still unchanged. So the remaining part is this. Voltage drop across internal resistance, across armature resistance, which is here. Armature resistance is very low, much more less than 1 ohm, but it still exists. Therefore, we start to subtract slightly, some few volts, and therefore speed starts to drop slightly. Okay, let's apply rated torque of 0.4. 0.4 Newton meters. Okay. This is the rated torque. And this is the no load. Because we have 0. Yeah? So rated torque. At the rated torque we have to consume rated current 5.4 amperes. As you can see, rated current is 5.4 amperes. And the speed also should to be rated approximately 200 RPMs. Let's check. Not near to this, yeah. Okay. Yeah. So let's reduce the supply voltage. And I will also put the brake to the minimum. Yeah. Okay. As you can see, Shunt-wound DC motor has very strong characteristic. If I will show it here, then at zero torque we had 2300 RPM, so somewhere here. Yeah. And at 0.4 torque we have approximately 2000. So, as you can see, this drop is very small. Very. Typically, this drop is about 5 to 10% only. What about current? Current is equal to the rated at the rated torque. Therefore, we are not able to go here. Yeah, we are not able to go here because here we will got current which is higher than rated. So this is the overload, so the motor becomes too hot and it will not be able to operate. Okay. Now another question. What will happen if I will tend to start the motor without field? First of all, let's take a look how it is started when I slowly apply voltage and the field is maximum as it should to be. Look. I apply voltage and the armature current increases too. Yeah? Everything is good. And now back to the zero. Okay. Now I will remove field. From this equation we can see that if field is very low, actually there are no field current, but there is some little field which comes from the residual magnetism of the iron. Yeah. Therefore field is very little, so the armature current must be very high in order to produce at least some little torque. So let's see. I will increase without the field, I will increase supply voltage. Where's the focus? Okay. So I increase the voltage, so the current increases, but there is no rotation. Now we got overload because 5.4 amperes, this is the maximum. And maybe if I will help them, then it will start to rotate. But with really high overcurrent. So this is the real problem, so we can burn the motor. That's why we have to start motor with field. Look. I apply field and it starts to accelerate. So we have to start with maximum field as possible. And now we have no problem with acceleration. Okay. So now let's try to adjust speed of this motor. From this equation we can see that we can adjust speed by means of supply voltage or by means of field. As you can see, speed is directly proportional with the supply voltage. Let's check. Again, maximum field, starting up. So actually, I'm able only to reduce supply voltage because I can't increase it for more than the rated voltage. So at no load we have 200, 2300. Now I will reduce voltage from 20 to 15. From 20 to 15 give us 1700. So as you can see, everything is proportional. Yeah. Everything is proportional. Another way how to control speed, this is the adjusting field. Field can be adjusted by means of field reset. As you can see, if I will reduce field, then speed will increase. Let's check. Yeah? So, at the field of 2.5 amperes, speed is field is 2.5 amperes, speed is 2300, and if I will reduce field, for example to 1.8, the speed increases, and now it is 2700. Okay, very good. And now let's take one joke. Look, it's operating at the maximum field. If I reduce the field, the motor will accelerate. It will take more current from here, yeah, and it will accelerate. Yeah. But what will happen if I will momentarily increase field? Look into the current. It becomes negative. It becomes negative because when I increase field, I increase back EMF, which is in the armature and which is directed in opposite direction with respect to the current. So I increase field, this back EMF increases too, and therefore current starts to flow in the opposite direction. So the motor again becomes a generator for some small time when we have inertia, and when it slows down, again it becomes a motor. So like a recuperative braking, isn't it? Okay. So now let's take a look how series wound motor performs. In a series wound motor, field winding is connected in series with armature winding. Therefore, through the series winding, we got armature current. Yeah, this is the same current, and therefore we have only 1 ampere meter. So if I will switch this motor into the series, then this rheostat becomes disconnected. As you can see, yeah, it doesn't work because now field current, this is the armature current. So we will see only armature current, which is also field current. So as we can see from here, at low load we have very low armature current. Very low armature current will produce very low current through the field. Therefore, field will be very low, and therefore speed will be very high. Therefore, series wound motor cannot be started at no load because it will cause overspeed. That's why I will apply some brake. And now I can safely start it. So let's put our torque back to the rated on 0.4. Okay. So now armature current is equal to the rated current 5.4. Again. What about the speed? The speed is much more slower. 1500. If I will reduce brake, armature current will reduce, and therefore current through the field winding also reduces, and therefore speed will increases. Let's look back to the 0.2. Armature is 3.8, and the speed 2200. So now we are operating at much more higher speed than we have than the rated speed. Yeah. So actually we are not able to operate at no load at all, because it will cause very high overspeed of the motor. Let's try. Yeah. So 0.1 give us 3000. With very little current. Therefore, this motor is not able to operate at no load at all. It will cause overspeed, which will be here. So, many times in the books you can see that they write that series wound DC motors are able to produce very high torque. Let's check, is it true or not? So I approach the maximum of the torque meter, yeah, 0.7, and as you can see, speed is very low, 0.7, and the speed is very low. What about current? Current is more than the rated current. So where is the high torque? You may say that, look, here is the high torque, yeah? But how do you think? Does the shunt wound motor is not able to produce 0.7? Let's check. Again, maximum field. I can start shunt without the brake, so I can just apply the voltage. And now let's apply 0.7 torque. Let's check, is it possible to do this or not? Yes! As you can see, it is possible, or even more. Yeah? But the problem is that the motor does not slow down. Oh no, sorry. It was 1900. But what about the current? Current is very high. So the joke is that both motors, both shunt and series motors, are able to produce very high start torques. But the difference is that if you will apply very high torque to the series wound, it will slow down. And this slow down will help us to keep current reasonably low. So, very low speed during starting, and current also is not very big. However, here Just imagine what current will be if it would be on the speed of, say, 500 only. So the current will be maybe 50 amperes or even more. So this is the joke. Both motors are able to produce very high start torque, but shunt-wound motor will damage itself and will damage supply network because of very high armature current. So if we will show this by the red color, this torque speed characteristic of the series wound motor on this characteristic, then we will see that 0.7 do not have, 0.4 give us speed of this, yeah, and 0.2 give us 2.2, 0.2 give us 2.2 somewhere here, and further we got overspeed. So the characteristic looks like this. So as you can see, we can get overspeed and we can get overcurrent, yeah, but overcurrent is not the problem. The problem is that we are not able now to work below this torque. So we are not able to work at no load. Yeah, series wound motor is not able to work at no load. So these are general differences between two types of motors. Shunt wound has very stable RPMs. It is able to operate at no load. It is able to operate at the rated load. But during starting, if high load torque is applied, then it will consume very high currents and therefore it will be damaged. Series wound DC motor is able to slow down during high overloads and therefore it will consume less current and it will most probably survive. From other side, if we will reduce torque towards no load, then it will cause overspeed. Therefore, series wound motors can operate only in applications where it's not possible to operate at no load. So